Okay, are we recording? Yep. Okay, cool. So, another update. So last time, I was sick yesterday. Spoiler, still sick today. So we won't be meeting today either. This will be actually our last class, so you won't be meeting me again. Next week will just be a study week, so you can reach out to me if you have any questions about the material, and if you need to meet with me, we can set up a time to meet, but otherwise it will just be a study week. We won't have any scheduled class meetings per se, because otherwise it's just review of the material, and I just want you guys to be able to study. The final, for those of you who opt in to take it, will be take home. Kind of just like this. I'll have it actually graded through, I'll have it posted through Cengage, I believe. I'm working on that right now, is the method I think I'm going to do it. So it will be graded immediately. So you'll be able to do it as soon as you want and have it graded immediately. So you'll have that information. And so if you have not already done so, go and opt in or opt out of the final exam. You have to go choose what you want to do, right? So choose whether you want to take the final or whether you don't want to take the final. I have it outlined on how that happens. You go to, let's see, you can go to, let's do the student Canvas. Student Canvas. If you go to our Canvas page, I load this, I go here. Under exams, there should be this final opt-in, opt-out quiz. I'm not going to click on it because I don't know if it shows students' answers, and I want it to be anonymous so nobody sees anything. But you click on that, and you can just click on whichever option you want. But you have to do that by tomorrow at noon. So make sure you go do that, okay? Do that as soon as possible. Other than that, we don't have class tomorrow. I've canceled class so that you guys can enjoy your Independence Day holiday. So that means that the class is not going to officially cover limits and derivatives. We'll see how fast I go through material today. I might, if I go through geometric series and induction pretty quickly, I might cover some limits, but your final won't include limits, so you don't have to worry about that. It's not going to be included, but I might go ahead and lecture it so that you see it at least. Okay. So let's go ahead and get started on actual material. So let's see, geometric series and induction. So last class we talked about sequences and series, and specifically we talked about arithmetic sequences and arithmetic series. So that was, like I said, we can have all sorts of different sequences, and sometimes we can come up with formulas for our sequences. Oftentimes for the sequences we can come up with formulas, but for the series, for the nth partial sum, that's really hard to do, and in most cases you can't do it. For a couple cases you can, and those couple cases that are easy are arithmetic sequences. So that's what we did. So we did arithmetic sequences here, that were sequences where each term had what was called a common difference. So right, each term had a common difference, and so we generated the next term by just adding some constant difference d to each term of the sequence, right? And the next one that we're going to learn about is called a geometric sequence, and it's analogous to the arithmetic sequence in the sense that a geometric sequence is such that each term is a constant multiple of the previous. We call this term the common ratio. So a geometric sequence is any sequence of the form a, ar, ar squared, ar cubed, ... arn ... all the way off to infinity, right? So we call the first term a, right? A is the first term of the sequence, r is the common ratio, and the nth term of the sequence is given by ar to the n minus 1. So an is ar to the n minus 1, right? Because a1 is AR to the 1 minus 1, which is AR to the 0, which is anything to the 0 is 1, right? So A1 is equal to A, which is equal to AR to the 1 minus 1, which is equal to AR to the 0, which is equal to A times 1, which is equal to A. Right? Anything to the 0 is equal to 1. Well, besides 0. 0 to the 0, undefined. Sometimes we define this to be 1. Sometimes. But that's not important, right? So you can ignore this information here. Sometimes it's useful to define that to be equal to 1, but for most purposes, it's considered undefined. It doesn't really make sense. Okay, so anything to the 0 is equal to 1. Right, and so we'll just go through this kind of like what we did with arithmetic sequences, and we'll look at this. And the nice thing about this is arithmetic sequences, we can't add up infinitely many terms, right? If I add a common difference, for instance, the natural numbers, if I add up the natural numbers, 1 plus 2 plus 3, right? Arithmetic sequence 1 plus, or 1, 2, 3, 4, ... and then I did the arithmetic sum S n equals 1 plus 2 plus n, right? I go up to n, and this is equal to, remember, this was the sum from I equals 1 to n of I, right? If I did this, if we did this for infinitely many, right? If I did like S infinity, this would equal infinity, right? This doesn't really make sense, right? We can't add this up and get a finite number. But what we're going to find is that with certain geometric series, we can actually do this for infinite. We can add up an infinite amount of things and get a finite number, which is actually kind of insane when you think about it. And we saw an example of this last class where I was talking about that Achilles paradox. So if you looked into that, maybe you are maybe going to see where this is kind of going. But if not, we'll cover it, so it's okay. Okay, so anyways, let's get started. So let's do some examples just to get us familiar with these arithmetic sequences, or these geometric sequences. So consider the sequence with A equals 4 and R equals 3, right? Write out a few terms of the sequence and then compute the 70th term, right? So our sequence is AN from n equals 1 to infinity. This is also, just to refresh our notation, n in n, right? This is also equal to a sub n, right? These are all equivalent notations, but now we can actually write out the sequence. So our first term is 4, and we have a common ratio. So I go 3 times up from 4. So I do 4 times 3 is 12. 3 times 12 is 36. 36 times 3 is, well, 30 times 3 is 90. And 6 times 3 is 18, so this is 108, comma, and then a few more terms, right? And so I only asked for a few terms, so we'll say 4 is enough, right? And so it just keeps going on, right? And we want to compute the 70th term. And so, well, I have this formula right here, right? We have that a sub n equals AR to the n minus 1. So that implies that a sub 70 is equal to AR to the 70 minus 1, which is equal to, right, 4 times 3 to the 69, right? And if you calculate this out, this is approximately equal to 3.3 0.37 times 10 to the 3, right? So 3,337. I don't know why I'm saying approximately. That's probably exactly equal. Let's see. Let me plug this into Wolfram Alpha real quick, see if I got that right. Wolfram Alpha. That sounds a little wrong. 3 to the 69 sounds like a huge number. 3 to the 69 should be much bigger than 3,000 times 4. Oh, yeah, that is definitely wrong. This is 3.33 times 10 to the 33. Right. So that's a lot bigger, right? Okay, so it's about that big. So grows pretty quick, right? Just after 70 terms, I think that's more atoms than there are in the universe, right? So how many atoms in the known universe? Not quite. Okay, there's 10 to the 79 atoms. Okay, we'll ignore that. Okay, so anyways, but it grows really fast, right? So geometric series can grow really, really fast, especially if their common ratio is bigger than 1, because we're exponentiating it every time, right? We're raising it to a power every single time. So as that gets bigger, it starts getting bigger much quicker, right? So let's consider this term, right? So before I gave you the starting value and the common ratio, and I asked you to find a certain term. Now I'm going to give you terms, and I'm going to say, what is the common ratio? What is the starting term? What is the formula for the nth term, right? And so here, well, we can say, well, what's the common ratio? So we can say, well, the common ratio is given by, well, just the ratio of any two terms, any two adjacent terms, right? So take any two, take the ratio of any two adjacent terms. So if we do that, we could do, so r is equal to 12 divided by negative 4. This is equal to negative 3, right? You could also do r is equal to negative 36 divided by 12. This would also be equal to negative 3, and so on and so forth, right? You would always get negative 3, right? Because they all have the same common ratio. That's why it's common, right? So it doesn't matter which two you pick. You just have to pick adjacent ones. So we get that the common ratio is that, and then, well, to figure out what the nth term is, we have the formula. The nth term is given by a sub n equals a times r to the n minus 1. We have r, so that's known. This is unknown. Is it? It's not really unknown, right? It's right here. It's negative 4. It's the first term in the sequence. It's the first term. Right? So a sub n is equal to negative 4 times negative 3 to the n minus 1. And you'll notice that, well, this series, notice, it's alternating. Negative to positive. Right? So, well, why is that? Well, look, I can factor out a negative 1 here. We can write this as negative 1 times negative 1 So I could write this as -1 times, let's say, 4. And then I could do -1 to the n minus 1 times 3 to the n minus 1, right? So I split up this one here, and I split up, so maybe I should color code these. So I split up this one here, and I split up this one here, right? And so now that I have those, well, -1, now these guys, this one and this one combine, so we have -1 times -1 to the n minus 1, well, that becomes, this is equal to -1 to the n times 4 times 3 to the n minus 1, right? And so now I have my modifier, so we should have the modifier -1 to the n, right? That's what we decided last class. That was the modifier that shows up in these types of sequences. If it alternates from negative to positive, we have that modifier -1 to the n. And it turns out that even though it didn't look like we had it, because we had it written like this, it turns out that we do have it. It's just written in a funny way, right? And so we can always recover that by factoring that stuff out. Right? Okay, cool. So let's move on to the next example. Okay, so suppose we have a geometric sequence whose fourth term is 27 and whose eighth term is 2,187. What is its eighth term, right? So we need to figure out, well, what do we know and what don't we know? So we need to figure out what is its nth term. And so our whole goal here is to figure out, well, what's its common ratio and what's its first term, right? Because if we want to figure out its nth term, to find the nth term, we use a sub n equals ar to the n minus 1, right? So we need to find a and r, right? Those are two things that we don't know, right? So the first thing that we do is that we have the fourth term is 27 and the eighth term is 2,187. So what we're going to do is we're going to write that down. We have A4 equals 27, and we know that that's equal to AR to the 4 minus 1, right? And then we have A8 is equal to 2,187, and that's equal to AR to the 8 minus 1. And so these together give you that A4 is equal to AR cubed, and A8 is equal to AR to the 7th. Okay? So, what can I do? Well, I can say, well, maybe I can solve for R, right? If I want to solve for R with this, I can divide these. So actually, let's rewrite this as this is equal to 27, and this is equal to 2,187. So let's do, how do I want to divide these? I want to divide 3 over 7, so let's do 27 divided by 2,187 is going to be equal to AR cubed over AR to the 7th, right? I'm just literally taking these and dividing these two, right? And then what I get is I get this cancellation here, right? And I get 3 of these cancel with these, and I just get 4 down here, right? And so we get, this is equal to, so we get, I'm not going to reduce this at all. This implies that 27 over 2,187 is equal to 1 over r to the 4th and I want to flip this, so I get r to the fourth is equal to 2,187 over 27. And if I want to solve for r, we get r is equal to this, well, the fourth root, so we'll do 2,187 over 27 to the 1/4, right? Because I can raise this to the 1/4, and that cancels out this guy, and I can raise this to the 1/4. Right, there we get that. Okay, and so then we have r is equal to that, and if you do this, if you plug this into your calculator, you'll get that this is equal to 3. Okay, so we get that our common ratio is equal to 3. Well, now we want our first term. So how do we find our first term? Well, our first term, now that we have r, our first term can then be found using a sub 4 equals 27, which is equal to a times 3 to the 3, right? Well, 3 to the 3 is 3 squared is 9. 3 to the 3 is 27, which implies that 27 is equal to a times 27, which implies that a is equal to 1, right? And so now we have our first term and our common ratio. So our common ratio and our first term here. And so now we know that our nth term is given by this formula with these two quantities, right? And so given some information, you can fiddle around with them to work up to it. Okay, so that's kind of exactly what we did last class with the arithmetic sequences. So it's very similar to what we did last time, right? And so now we're going to move on to partial sums, right? So I give you that whole story about Gauss and about how he added up those numbers from 1 to 100 for the partial sums of the arithmetic sequence. Turns out that the same trick works for the partial sums of a geometric sequence. So recall that the nth partial sum, Sn, can be written in sigma notation as the sum from k equals 1 to n, right? So this is the sum, sigma. So let me write it out and then I'll go over it. A r to the k minus 1 is equal to a plus ar plus ar squared plus ar cubed plus dot 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 plus ar to the n minus 1. Okay, so let's go over this real quick. So the nth partial sum, Sn, is equal to, the way you read this is the sum from k equals 1 to n of a r to the k minus 1. And why is it ar to the k minus 1? Well, a is the first term, right? Remember that the sum for a sequence means an, the nth partial sum. Let's call this, maybe use a different ak. The nth partial sum is Sn equals the sum from k equals 1 to n of ak, right? So that's in general. And look, a sub n, so in this case we write this as a k, a sub k is equal to a r to the k minus 1. So we put that there. And if you just write out a couple of these terms, when k is equal to 1, this is a r to the 0. So this is just a plus AR to the 2 minus 1 is 1. So this is AR to the 1, which is just AR. AR squared, AR cubed. Okay? And then we use a very similar idea to what we did for Gauss's method, and we consider this difference. So we write Sn is equal to A plus AR plus AR squared plus dot 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 plus AR to the n minus 1. And then we minus from it now RSN. So we multiply each term by R, and what that does is we shift. So I do a minus, now this is AR, minus AR squared, minus dot dot dot, minus AR to the n minus 1, but now I also minus an AR to the n, right? I go up one more because I added an extra R. So instead of going up to AR to the n minus 1, I go up to AR to the n because I multiplied by this R, right? And so now that I do that subtraction here, we get, well, here we get S minus RN, oh, sorry, RSN is equal to A minus AR to the n, right? Because this one cancels with this one cancels with this, all these cancel here, this one cancels here, and we're only left with this one minus this one, right? Well, this has an S in there. Well, look, we can factor out this. So this implies that Sn times 1 minus R is equal to A minus AR to the n. So maybe actually let's factor out the A times 1 minus R to the n. And then, well, look at that. That means Sn is equal to, just divide both sides by 1 minus R. A times 1 minus R to the n over 1 minus R. And now we have a formula. So this is the formula for the nth partial sum of a geometric series, or of a geometric sequence. So, theorem for a geometric series defined by an equals AR to the n minus 1, the nth partial sum, Sn, is equal to A plus AR squared plus AR cubed plus, with R not equal to 1, is equal to this. So why can't R be equal to 1? Well, of course, if R is equal to 1, then Sn is equal to infinity, right? This blows up. I get division by 0. I'm not allowed to do that, of course. And what does that, why is that the case? Well, look, I get 0 over 0, in fact. I get 0 divided by 0. That doesn't make any sense. That's an indeterminate form is what we call it. So we don't allow R to be equal to 1 in these common ratios, because that's just taking A plus A plus A plus A plus A plus A plus A. That's not considered a geometric sequence. Okay? So let's consider the following partial sums of this geometric sequence. So let's do some examples, and I think that will help illustrate these problems. So to figure out what these are, we just need to write out, it's often useful to just write out a couple terms. Sometimes it's written out for you, sometimes you have to write it out. And then identify all the key points, right? We need the first term and the common ratio, and then we can figure out the nth term. So what's the first term of this? Well, it's just literally the first term. So the first term is R equals 1. The common ratio is the ratio of any two adjacent terms. So let's do just 3 divided by 1. This is equal to 3. And you could also do, of course, 9 divided by 3. This is also equal to 3. You could do 27 divided by 9. This is also equal to 3, right? You don't have to do that. You just pick one. Cool. So the common ratio, let's say R is equal to 3. Okay. Oh, first term, I don't know why I said R. This should be A, right? A is equal to 1. The first term R is, what's the value of the nth? Of the partial sum. Oh, what's the value of the partial sum? This, let's see. I think this is what I meant to say. This is the 8th term. Okay. Yeah, that's the 8th term. So the 8th partial sum. Okay. So we want to add up all the terms, see what the value is of the 8th partial sum. So the first term, so Sn is going to be equal to A times 1 minus R to the n over 1 minus R, which implies that S sub 8 is going to be equal to 1 times 1 minus 3 to the 8 over 1 minus 3, right? And so this is equal to 1 minus 3 to the 8 over negative 2, which ends up being equal to negative 6,560 divided by negative 2. Ends up being 3,280. All right, and so once you identify the first term and the common ratio, it's very easy to get these values. Okay, so the finite series are not that interesting. It's kind of boring. So, but what if we want to add up all of the terms of a sequence, right? So I give you an infinite sequence. Okay, I ask you to add up finitely many. That's kind of useful maybe, but it's really interesting to talk about, can we add up infinitely many things? Your first implication might be, who cares? If I add up an infinite number of things, the final result is just going to be an infinite number, right? No matter how small the thing is, if you add up infinitely many of them, it's infinite, right? You're going to get an infinite number. Well, it turns out that that's not actually the case, and in fact, in many cases, we can add up an infinite number of things and reach a finite value. In fact, we can reach very small numbers, right? So to discuss this, we're going to go over some vocabulary, right? So if the value of Sn goes to a finite number S, so Sn, if as n goes to infinity, the value of Sn approaches this number S, whatever it is, as n gets big and bigger, we say that the infinite series converges, right? It converges to this value S. In particular, we say it converges to S. If instead Sn does not converge, then we say it diverges, right? We will often say that Sn approaches S as n goes to infinity, if it converges, right? If it converges, then we say Sn approaches S as n goes to infinity. This is vocabulary of like limits, okay? This is really a statement about limits, but we'll cover that in the next chapter. Like I said, the notation you'll see and use is that Sn goes to S as n goes to infinity, right? So if this says Sn goes to S as n goes to infinity. Okay, so as n gets big, Sn approaches S. It's never S. It's never quite S unless we take this all the way out to infinity. But it's getting closer and closer and closer to S, right? So we say in the limit, it ends up being S. So it's like if you're looking at an asymptote, right? So if I have a function and it asymptotically approaching the x-axis, it never quite gets to the x-axis, but if we went all the way out to infinity, it would touch the x-axis, right? So it's getting closer and closer and closer to the x-axis, and so we say the limit would be the x-axis. So we say this function converges to the x-axis, okay? And so geometric series are the first ones that you can talk about whether these things converge or diverge, right? So we already know the form of a geometric sequence, and we now construct an infinite geometric series. So we want to sum up every term of our geometric sequence. This just means that we want to compute the following. So now our sum, it's the sum from k equals 1 to infinity of ar to the k minus 1. This is just equal to a plus ar squared plus dot 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 plus ar to the n minus 1. This is the nth term plus off to infinity. So this is the nth term. This is off to infinity. Right. So we know that the nth partial sum of this series is given by this formula here, right? So what can we say as n goes to infinity? So we don't really have the idea of limits yet. So this is kind of tongue-in-cheek. We're kind of just playing games here. We're not being precise, but the intuition here, I think, is all available to you guys. And so what do we want to? We want to think about what can we say as n goes to infinity? Well, we want to look at the behavior of this function. So, well, when r is greater than 1, what happens? When, that doesn't look like when, what happens? Right, so when r is greater than 1, what happens? Well, r to the n gets big fast, right, as n gets big. Right? So if r to the n gets really big, right, this gets really big, that shoots up. R to the n gets huge, right? 2 squared is not that big, it's 4, but 2 cubed is 8, and then 2 to the 4th is 16, and then 2 to the 5th is 32, and then 2 to the 6th is 64, and then 2 to the 7th is 128 or something like that, right? It's getting big really quick, right? So this is blowing up really fast. So what's happening is I'm taking 1 minus a really big number, right? Divided by, well, who cares how big this is, right? R. If R was even just slight, like I said, like R is equal to 2, then 1 minus 2 is just negative 1, right? That's not that bad. This is going to blow up. This is going to keep getting bigger and bigger as n goes to infinity. And so Sn goes to negative infinity as n goes to infinity, right? Because I keep on subtracting a bigger and bigger number. I go as long as my first term is if a is positive, right? Just assume that a is positive. It doesn't really matter. If a was negative, then this goes to positive infinity, but just assume that a is positive, right? And so I take 1 minus a really big number that's negative divided by this, end up going to oh no, this will go to positive infinity, sorry, plus infinity, right? So I take 1 minus a really big number is negative. R is greater than 1, so 1 minus something bigger than 1 is also negative. So I get a negative over a negative. It's positive. And so, anyways, I get something really big, right? 1 minus a really big number is a really negative number divided by something small. It's still a really negative number, but this number is also negative, so the whole thing's positive, so then it's a really big positive number, right? Anyways, so similarly, if R is less than negative 1, then Sn goes to, well, what direction does Sn go to now? Well, if R is less than negative 1, then what happens? So I'm adding something here. So if R is less than negative 1, then I start adding positive numbers, right? So this again grows really big. So it's either very, very negative or very positive, depending on the sign, depending on whether n is even or odd, right? And so this still goes to plus or minus infinity as n goes to infinity, right? In either way, when n's big, right, or when n is bigger than 1, when I start squaring it, cubing it, taking it to the fourth, right? So if I did, like, for instance, I don't know, let's do, yeah. So like 2 squared, like I said, is 4. Squared is 8. Squared is 16. Squared is 32, right? It's growing bigger and bigger. And anything bigger than 1 is always going to do that. 1 is going to stay the same no matter what I do. 1 squared, 1, let's say 1 is equal to 1 squared is equal to 1 cubed is equal to 1 to the fourth is equal to blah, blah, blah is equal to 1 to the 879,642, I don't know, whatever, right? Is equal to dot, dot, dot. It doesn't matter how many times you take it up. 1 doesn't change. But as soon as you go over 1, it starts growing. And as soon as you go under 1, it starts shrinking, right? 1/2 is greater than 1/2 squared, which is equal to 1/4, right? Which is greater than 1/2 cubed, which is equal to 1/8, which is greater than 1/2 to the fourth, which is equal to 1/16, right? Dot, dot, dot. All right, so as soon as you go under 1/2, it starts shrinking, okay? So we see that basically, so when the absolute value of R is greater than 1 or equal to 1, then Sn diverges. If the absolute value of R is less than 1, then Sn converges. Okay. Because what happens is, just as when it's greater than 1, this number gets really big really fast. When it's less than 1, this number gets really small really fast. And so this number ends up going, this whole thing ends up going to 0. Okay? Okay, so so this thing goes to 0, and so if absolute value of R is less than 1, then R to the n goes to 0 as n goes to infinity. So Sn goes to a times 1 minus 0 over 1 minus r, which is just equal to a over 1 minus r, right? As n goes to infinity. So in fact, not only does it converge, but it converges to this value, right? So now we have a formula specifically for the infinite series. Not only can I tell you that it converges, I can tell you exactly what it converges to. It converges to this number, right? And so we have this formula here. So this is our theorem. It says if r is less than 1, if the absolute value of r is less than 1, then the infinite geometric series ar to the n minus 1 from k equals 1 to infinity converges to s, which is equal to a over 1 minus r, or just writing it all out. If alternatively r is greater than 1 or equal to 1, then the series diverges, right? If r is equal to 1, then this is just summing up a's, right? So let's maybe correct this. If this is greater than or equal to 1, then the series diverges, right? So let's see. So determine if this geometric series converges or diverges. If it converges, what does it converge to, right? So this goes back to, this is the Achilles paradox. Again, from last class that I talked about. It says that if I want to travel, like, if I want to say, oh, I want to travel from the finish line, right? From the start to the finish, I have to go from here to here. I have to travel half the distance, right? Like, to get to the end, I have to go half the distance. I must, right? But also, once I've traveled half the distance, I still have half the distance to go again, right? So I still have to go half the distance again. Well, and then to go half the distance again, like to get to the end, I still have to go half the distance again. And then to get to the end, well, I still have to go half the distance. And then to get to the end, I still have to go half the distance. And then to get to the end, I this is my little flagpole. I still have to go half the distance, and I still have to go half the distance, and half the distance again, and half the distance again. And then I keep having to half these distances. And Achilles, or whoever thought of this paradox, said, how on earth am I ever getting anywhere? Because I always have to go half the distance to get anywhere, right? Every time I go somewhere, I have to cover half the distance to get there. In each step, there's another half distance to cover. So how do I do that? And this geometric series actually shows you that we can cover an entire distance with infinitely many steps. And this says that you have to do it in infinite time. You can't do it in finite time, but it turns out that, of course, we can do it in finite time. So anyways, it's an interesting paradox. It's an interesting thought process, but let's do the problem. So it says, determine if the series converges or diverges, and if it converges, what does it converge to? Well, what's the geometric series? So, well, first we should say, what's the first term? The first term. So one thing you'll find is that we can figure out what the common ratio is pretty easily. You'll be able to see it from looking at these a lot of times, but we can just write out a couple of the terms. So let's say we could say the sum from k equals 1 to infinity of 1/2 to the n. This is supposed to be to the k. That's a typo. This should be to the k. Is going to be equal to, well, this is 1/2 to the 1 plus 1/2 squared plus 1/2 cubed plus ... right? So the first term is 1/2, obviously, right? So this is equal to a. So we have our first term is a is equal to 1/2. Okay? And we want to figure out our common ratio. Well, for this one, it's pretty easy to figure out the common ratio. The common ratio, we just take two adjacent terms, and we could say, well, this is equal to, right, 1/2 plus 1/4 plus 1/6, right, plus ... or sorry, not 1/6, 1/8 plus ... right? So r is equal to 1/4 divided by 1/2, which is equal to 1/4 times 2/1, which is equal to 2/4, which is equal to 1/2. Right, so the common ratio is 1/2. And that makes sense, right? Because this also, we could say, note that this sum, 1/2 to the k, must be equal to, this must be equal to a times r to the k minus 1. Right, and so we want to solve for r, and we know that the first term here is 1/2, so that we have that implies that 1/2 to the k is equal to 1/2 times r to the k minus 1, which implies that now divide by 1/2, and so we can use properties of exponents, 1/2 to the k minus 1, right, because we divided by 1/2, so we just subtract 1 from the exponent, r to the k minus 1, so that implies that r is equal to 1/2, right? That's another way that you could have done it. So there's a lot of ways that you can also do it. And so you get this. And so what does it converge to? Well, s is going to be equal to a over 1 minus r, which is equal to 1/2, divided by 1 minus 1/2, which is equal to 1/2, divided by 1/2, which is equal to 1, right? Anything divided by itself is just 1. And so it turns out that you actually do converge to your final distance after you complete the infinitely many steps. And so we've somewhat resolved Achilles' paradox. Except for it took us infinitely long to do it, right? And so there's still some questions there on how do we resolve that. But that's philosophy. Go take a philosophy course. Okay, so let's look at maybe a little bit more complicated of a geometric series. So I give you this, and we want to know whether this converges or diverges. Now, for the first one, you could read off the common ratio, right? It's just 1/2 to the k. Of course, everything was just 1/2. We started at 1/2, and we were just multiplying it by 1/2 every single time, right? So the common ratio is 1/2, so you know it converged. Here, I don't have common exponents, so I don't know what the common ratio is initially, right? So I want to figure out what the common ratio is. And so what I'm going to do is, what I recommend you do for right now is just write out a few terms. If your algebra skills are great, then you can figure out the common ratio. But you'll need to figure out the first term anyways, so you're going to have to write out a couple terms, at least one term anyways. So the sum from n equals 1 to infinity of -2 to the n minus 1 over 6 to the n is equal to, well, -2 to the 0 over 6 to the 1 plus -2 negative 2 to the 1 over 6 squared plus negative 2 to the 2 over 6 cubed plus dot dot dot. Don't really want to go higher than that because I don't know what's bigger than, I don't know anything past 6 cubed. So negative 2 to the 0 is 1 over 6 plus negative 2 to the 1 is negative 2 over 6 squared. 6 squared is 36. Negative 2 squared is 2 squared, which is 4 over 6 times 6 is 36. 36 times 6, well, 6 times 3 is 120. And then, no, 6 times 3 is 18 plus 6 times 6 is 36. So 180 plus 36 is 216. Plus dot dot dot. Okay? So we have that. Okay. So the first term is 1/6 equals A. Cool. Done. Common ratio just take negative 2 over 36 divided by 1 over 6. Okay, remember what order you need to take these ratios. You need to take the leading term, right? So we take, I keep doing a lot of gestures with my hands and you guys don't see them. So you need to take this term divided by the previous term. So the leading term divided by the previous term, right? To get the correct ratio. Because if you take this term divided by this term, well, that's not the multiplication that you want, right? We want to figure out what are we multiplying this by to get this. And to do that, you divide this one by this one, right? Well, that's just equal to negative 2 over 36 times 6 over 1. Well, this is equal to negative 12 over 36, which is equal to negative 1 over 3, right? Which is equal to R. And so we check, does it converge? Does it converge? Yes. Absolute value of R is equal to 1/3, which is less than 1. That implies converges. So S is equal to A over 1 minus R, which is equal to now 1 over 6 divided by 1 minus negative 1/3, which is 1/6 divided by 1 plus 1/3. So this is 1 over 6 over 3/3 plus 1/3. 1 over 6 over 4 over 3, which is equal to 1 over 6 times 3 over 4, which is equal to 3 over 24, which is equal to 1/8. Right? And so we know that this series converges, and it converges to 1 over 8. So, in fact, we're adding up infinitely many terms, but we're converging, in fact, to very small numbers, 1 and 1/8, right? So, in fact, not only do we add up infinitely many things, but we don't get very large numbers. We're getting very small numbers because these things are getting very small really fast. Okay, so that's it for geometric series and geometric and infinite series. Next, I want to move on to a section called mathematical induction. So this is kind of your first foray into what math kind of really is. So math is all about logical reasoning and proving things. So the beauty about math is that our laboratories are on pencil and paper, sometimes in a computer, and we reach a level of certainty that all the other sciences wish they could reach, right? So once we've proved something, it is always true forever. So, I mean, the other fields of science, they're very robust, they're very rigorous. Newton, he proved his theory of gravity a long time ago, hundreds of years ago. It withstood the test of time until about 150 years ago. Einstein came through and he said, actually, let's change it. It's incomplete. General theory of relativity needs to come through. We need to modify it. Euclid, however, came out, had the theory of geometry, of Euclidean geometry, 2,000 years ago. And it is just as true today as it was back then, right? So once we prove something in math, it is true always and forever, no matter what. There's nothing that we can do to unearth it. We can change our assumptions of a system to change results, but under the assumptions that we make, it is always true no matter what. There is no measurement that we can make that will unearth stuff. So it leads us to very robust and rigorous results. And mathematical induction is this beautiful proof technique that allows you to prove some really powerful results. And so we're going to talk about it. Right, so in this section, we'll expose you to your first proof technique. It's called mathematical induction. Proofs to mathematicians are lab experiments in any other STEM field. I just went over those. Mathematical proofs is to say that unequivocally something is true. Once you have proven something, there's no new information will ever arise to demonstrate it is false. So we can consider the example from your textbook. So they conjecture, I actually don't know if this is still in your textbook. So they conjecture that 1 is equal to 1. Okay, that makes sense. Yeah, of course. And then they say, okay, well, 1 plus 3, we're going to add up all the odd numbers, and we're going to conjecture a formula. Conjecture means guess. It's a fancy term for guess. And then 1 plus 3 plus 5 equals 9, right? And then 1 plus 3 plus 5 plus 7 equals 16. Okay, and then 1 plus 3 plus 5 plus 7 plus 9 equals 25. And so they say, well, this is equal to 1 squared. This is equal to 2 squared. This is equal to 3 squared, 4 squared, and this is equal to 5 squared. So we're going to conjecture, I guess, fancy term for guess, if you ever want to sound pretentious, the sum of the first n odd numbers is n squared. Or we can write it in our sigma notation, the sum from k equals 1 to n of 2k minus 1 is equal to n squared, right? So this is our conjecture. Now, this is a guess. We made this, right? I could check this for 47 trillion cases, right? I could check this for the sum of the first 47 trillion odd numbers, and it could still always be true, right? That is not enough, right? Right? We have to prove it for everything. 47 trillion is a drop in the bucket for infinity, right? It's nothing. It's barely anything in terms of infinity. It's nothing, right? It might as well be 1, right? And so what we use is a method called mathematical induction, and it's a way of bootstrapping a proof. The general method basically is as follows. So suppose we have a proposition that depends on n, right? So we'll call this proposition P of n, right? So this proposition says our proposition is the first n odd numbers, right? So this proposition depends on n, right? The first n odd numbers. We want to show that it holds for every n value, right? The way to do this is show that it holds true for a base case. I show that it's true for n equals 1. Well, we showed that that's true, right? We showed that 1 squared is equal to 1. Okay, so we already have the base case. Now, we're going to suppose it's true for some other case, k, right? Don't know what it is. Some other case, k. Suppose it's true for that. And if we can show that it's true for k plus 1, then we have shown that it's true for all n. And the idea here is, like, say I have a train, and I say, oh, I'm building a train, and I'm at the factory, and I have a rule. And my rule is that if I make, so, like, I'm building a train, and I have a rule, and I say, hey, oh, if I have a train, if I'm building a train, and I make a red train car, right? If I make a red train car, if I paint a red train car, every other train car I paint after that will be red, right? I will only paint red train cars after then, right? So, or how about this? Actually, if I paint a red train car, the next train car I paint will also be red, right? So if a train car I paint is red, the next train car will also be red, right? So if I paint a red train car, the next train car will also be red, right? For some train car, the next one is also true, okay? Well, we all know that the caboose of a train, the last train car or the first train car, whichever way you want to think about it, is red, right? Every train has a red caboose, right? So the first train car of all my trains is red. But I know after I paint a red train car, every other car is also red. Okay, let's see about stitching those together. I got a little interrupted. How are we doing time-wise? Okay, doing okay. So I was saying, every other train car is red, so the caboose is red. Every train car that I paint after a red train car is also red, so of course the whole train's red, right? So let's prove this claim. So proof. So we say the base case. 1 equals 1 equals 1 squared. Check. So now, suppose the result is true for some k. That is 1 plus 3 plus ... plus 2k minus 1 equals k squared, right? So the sum of the first k odd numbers is equal to k squared. This is called the induction hypothesis. So, induction hypothesis. Okay. We want to show the result holds for k plus 1, i.e. 1 plus 3 plus ... plus 2k minus 1 plus 2 times k plus 1 minus 1 equals k plus 1 squared, right? So, right, we assumed it's true for this. We want to show it's true for k plus 1. The k plus 1th odd number is this. We want to show that that's equal to k plus 1 squared. Well, we know that this, by our induction hypothesis, is equal to k squared by induction hypothesis, right? And k plus 1 squared is equal to k squared plus 2k plus 1, right? So we get k squared plus 2k plus 2 minus 1 is equal to k squared plus 2k plus 1. Well, and this side is equal to k squared plus 2k plus 1. And so this is equal to k squared plus 2k plus 1. Check. So by the principle of mathematical induction, the sum from k equals 1 to n of 2k minus 1 equals n squared for all n. For all n in the naturals is what we would say. And then we'd end our proof with a little box. All right, and so we can do these last two proofs and then we'll be done. All right, so let's do this. So again, we do the proof. So proof for any natural number, this proof. So the base case, this is n is equal to 1. So we say check. So check is 1 equal to 1 times 1 plus 1 over 2. This is equal to 1. Check. Cool. So we've done it for the base case, the induction hypothesis. Hypothesis is assume it holds for k, i.e. 1 plus 2 plus ... plus k equals k times k plus 1 over 2. And we want to show that what does it hold for. So let's see, 1 second. So we want to show that it holds for, we want to show it holds for k plus 1, i.e. 1 plus 2 plus ... plus k plus 1 equals k plus 1 times k plus 1 plus 1 divided by 2, right? This whole thing divided by 2. All right, and then we can say that this is k plus 1 times k plus 2 divided by 2. All right, we can write that a little bit more simply. Well, by our induction hypothesis, we know that this part right here is equal to k times k plus 1 divided by 2. And so what do we get? We get k times k plus 1 divided by 2 plus k plus 1 is equal to k we want let's factor out the k plus 1s. So k plus 1 here. There's a k plus 1 on both of these, right? K plus 1, k plus 1. And we can write this as k plus 1 times k over 2 plus 1. Okay, we have that. And then, well, we want, so I have my 2 showing up now, but I want this 2 here. So how can I do that? Well, the 2 needs to be dividing everything. So let's, so I want the 2 dividing this also. And to do that, I need common denominators. So we say that this is equal to k plus 1 times k over 2 plus 2 over 2, right? Which is equal to k plus 1 times k plus 2 over 2, right? Which is exactly k plus 1 times k plus 2 over 2. And so we're done, right? Because we've shown exactly what we wanted to show here, right? So check. Okay, and so by the induction hypothesis, or by the principle of mathematical induction, we're done with that. Okay. Now, let's do one more, and then we'll be all done. So, prove that 4n is less than 2 to the n for all n greater than 5. So, proof. So now, our base case is n equals 5, right? Because it says for all n greater than or equal to 5. So we have to check our base case is n equals 5. So check. So check. Well, 4 times 5 is equal to 20. And is that, well, 2 to the 5 is equal to 32. And that implies, is 20 less than 32? Yes. So check. So we're good with the base case. Okay? So induction hypothesis. Assume the result holds for some k. I.e. 4 times k is less than 2 to the k. We want to show then that it holds for k plus 1, i.e. 4 times k plus 1 is less than 2 to the k plus 1. Well, observe. 4 times k plus 1 is equal to 4 times k plus 4. But this is equal to 2, or this is, less than. We already know that 4 times k by the induction hypothesis is less than 2 to the k plus 4, right? But, of course, this is going to be less than 2 to the k plus 4 to the k, or 4 times k, right? Because if I multiply 4 by k, it's only going to get bigger, right? But then, again, by the induction hypothesis, that's less than 2 to the k plus 2 to the k. But that's equal to 2 times 2 to the k, right? But then that's equal to 2 to the k plus 1. And so now we're done because we have 4 times k plus 1 is less than, right? All of these are less than 2 to the k plus 1. And so now we're all done. Right? And so that's induction. It's a little tricky, but go through some examples and you'll kind of understand it. Okay, so that's all we have. I'm not going to go over limits. I don't think we have time. I don't think it's worth seeing necessarily, but let's go back over the announcements real quick before I send you off. So again, I was sick yesterday. Go ahead and opt in or opt out. There's no class tomorrow. We did not cover limits or derivatives. The final will not cover that. There is no class today, so do not come. Next week is a study week, so reach out if you have any questions, but we will not meet in class. Please opt in or opt out of the final now if you have not done so. If you do not do so by, I think it's tomorrow at noon, I will consider you opting out. I will consider you inactive in the course, and I will assume you have opted out. So I will choose for you if you do not choose by tomorrow at noon. So just do it now, okay? Do it now. Now. And then other than that, if you have any questions, of course, feel free to reach out and I'm happy to answer them. But I will post this, and other than that, you guys have a good rest of your summer, and I hope you guys enjoy it.